This problem talks about a wall, and there's a bar being held perpendicular to the wall by a wire. It goes like this. It tells us the length of the bar, which I'm going to call A, and the length of the wire, which I'm going to call C. And it asks us to find the tension in this wire. So that tells me already that I'm going to have to draw some forces. So I'm going to redraw the bar over here, and I'm going to draw in the forces. Obviously, we have the tension. That's what we have to find. So there's the tension going up at that angle. We have the mg, the weight of the bar itself, and that's going to be located in the very center of the bar and pointing downward. Now the wall over here, the wall may be pushing in this direction. It may be pushing up. It may be pushing down. It may in fact even be pulling that way. Depending on how the bar is attached to the wall and what's going on, there could be any number of forces here happening. So who knows what's happening there. So that, since I have some unknown forces happening here, that tells me I don't want to do force balancing. What I want to do is be clever with torques so that I don't have to deal with what's happening here. So I'm going to decide that this is my center of rotation and get rid of any torques that are caused by all of these forces and just deal with what's happening over here. So there's my center of rotation. Bye-bye all you unknown forces. And I'm going to draw in my lever arms for the forces that I do know about. So here, this lever arm number 1, we could call that, is for mg. And then lever arm number 2 is for the tension force. Now, lever arm number 1, that's going to be half of the length of the bar, and I decided that the bar had a length of A. So half of A. Lever arm number 2 is the entire length of the bar, so that's equal to A. So that's pretty good. Now I need to look at my angles. So the angle between R1 and MG, that's just 90 degrees, that's easy. But when I look at the angle between R2 and the tension, now I have something interesting. I've got an angle theta here, and I'm going to have to deal with it. So there we go. I've got my angles and my lever arms and my forces drawn out. So I'm going to go ahead and write the torque equation. I know that the total torque is going to be equal to 0. I've got this mg that's tending to pull the bar downward in a clockwise direction. I've got the tension that's pulling the bar upward in a counterclockwise direction. So I know that these two torques are of opposite sign. It doesn't matter which one I make negative, just as long as they're opposite signs. So the first one I'm going to say R1 mg. And the second one I'm going to make negative. That's going to be R2 times the tension times the sine of theta. And I know this has to equal 0. I can put in what R1 and R2 are. That's 1/2 A mg minus AT sine theta. But now I'm going to have to figure out what theta is. Let's go back to this triangle. Here's my angle theta. I know the length of the wire, and I know this. So I know two sides of this triangle. We could do a lot of calculation and actually figure out what theta is, but the fact is that we don't need to know what theta is. All we need to know is what sine theta is. If I call this side over here B, sine theta is B over C, right? Opposite over hypotenuse. So what is B with Pythagorean theorem? B squared is going to be equal to C squared minus A squared. So B is equal to the square root of C squared minus A squared. So that tells me that the sine of theta is equal to square root of C squared minus A squared over C. See that? So that's what I'm going to put in here. 1/2 AMG minus AT times square root of c squared minus a squared over c equals 0. And this is an equation I can solve. I know what c is, I know what a is, I'm trying to find what t is. That's my answer right there. I know the mass, I know gravity, I know everything except the tension, so I can use that to find the tension.